Welcome, everyone. Thank you for joining us for today's webinar, What to Know About Laboratory, Analytical, and Testing Methods, Expert Insights, and Other Considerations for Forensic Investigations and Failure Analysis, presented by Sean Berg. BakerRisk has decades of experience completing incident investigations, loss prevention studies, testing and research, and risk management services. We're excited to showcase in today's webinar services BakerRisk completes in our materials lab located in San Antonio, Texas. For today's webinar, I want to go over a few housekeeping items. First, we have posted links in the chat to content related to our webinar subject. We invite you to explore BakerRisk's published papers, webinars, and BakerRisk Training Center courses. Second, we want to respond to your questions following this webinar. Please type your questions into the Q&A box in the Zoom control panel, and our presenters will respond to the questions. Finally, at the close of our webinar today, please provide feedback by responding to our survey. And now for the webinar, Sean Berg will introduce and highlight how laboratory examination and analytical techniques can answer important questions during forensic investigations, failure analysis, and root cause analysis efforts. Sean is one of the BakerRisk Materials Lab and is a licensed professional engineer. He is also a certified fire and explosion investigator and is active within ASME, ASM, and NACE. So without further ado, I'm going to turn the time over to Sean.
Thank you, Naomi, for that introduction. And I want to welcome everybody to today's webinar, and thank you for attending today's webinar. I hope that you find this information useful and insightful, and maybe it'll give you some new things to think about with regard to what we will discuss today. And really, it has to do kind of with providing what laboratory analysis and testing methods can be used, and how essentially their importance, like what role they play in the examination of evidence or other items or artifacts that are recovered following an incident investigation or a loss scenario. And so I just wanted to cover focus really on cause and origin in FBA 921 and the forensic side of investigations. And then I also want to discuss failure analysis and prevention for more industrial settings and kind of tie that to fitness for service. So some things to take away, or really an overview, I would say. I just wanted to provide just a high level of what you can probably expect following an incident that occurs, in an industrial facility, whether that be a refinery or chemical plant, or it could even be a commercial building, could be any number of settings or properties in which an incident can occur. I want to cover the scientific method and also discuss basically how that plays into determination of cause and origin in an investigation. Just discuss basically the use of laboratory analytical and testing services to collect data and evaluate, just some of the findings and help us essentially develop hypotheses and determine, the final hypothesis, as well as drawing conclusions and providing recommendations in a scenario where we're assisting a facility, basically, and could be a turnaround or vendors or service related activities. And also, as it pertains to the forensic side of things, determination of cause, as well as determining culpability of a particular responsibility for a particular party. And then also, again, on the industrial side of things, basically the implementation of mitigation options to prevent failure that may have happened previously. So again, high level overview. I'm going to go over the use of a laboratory and in the evaluation of items that failed or evidence that's been collected following an incident. And this will basically include, basically just a little high level what to expect, as I mentioned, the different components of failure analysis, the different steps that you would generally take in a materials failure analysis, and how that plays into cause and origin. And I'm also going to discuss, essentially just, protocols and equipment and, just different expectations that you would expect, like in a laboratory Should you find yourself in that setting, you'll have an idea kind of how the different scientists and engineers will use the different methods to be able to collect data and evaluate a failure scenario. And I'll also provide some case studies to give you some information on how the process might look on the cause and origin side of things. So as I mentioned, cause and origin investigations. Before I kind of get into everything, I wanted to start with just putting out some terms. So it's important to distinguish between a few different things, and those specifically are failure analysis and prevention. What is meant by that? Well, essentially, without reading this entire slide to you, I'm just going to give you a high-level overview. In failure analysis and prevention, you have, let's say you're at a plant or a refinery and you have a loss of containment in a pressure vessel or a piping system. Essentially, this causes some downtime or it causes, an interruption. And so the question essentially is, why did it happen? And can we prevent it from happening? And what mitigation strategies can we implement? And what kind of repair can we do in this scenario? And so that could be determining if there's a corrosion mechanism or mechanical mechanism or an upset scenario. That's what failure analysis and prevention is. And it doesn't necessarily always have a forensic component to it, where you're going to be going through a legal proceeding. There is also a possibility of that happening, but essentially it just comes down to helping facilities run safely. And cause and origin is, really kind of aligned with that. Essentially what you're doing is these are the definitions that are put forth by NFPA 921 as it pertains to cause and origin. Cause is essentially the circumstances, conditions, or agencies that brought about or resulted in the event, such as a fire explosion incident. So NFPA 921 is more geared towards fire and explosion scenarios. Damage to property resulting from the fire explosion incident, or bodily injury or loss of life resulting from fire or explosion incident. So that's the way NFPA 921 defines it. And the origin is essentially the location, or really the origin at which, the fuel interacted, with the heat source in order to cause the fire explosion. So those are those definitions. Essentially what you're doing is you want to identify the origin or probable origins and then go through the process utilizing the scientific method in order to determine, cause or different causal or contributing factors in that scenario. Forensic typically will relate to legal proceedings. So when you refer to the word forensic, it could be criminal legal proceedings or civil legal proceedings. So typically, that's how forensic is used. It actually comes from the Latin forense. And root cause analysis is cause and origin essentially will feed into a root cause analysis. And a root cause analysis is something that's separate. BakerRisk has its own well-developed methodology for conducting a root cause analysis, but cause and origin is a component of a root cause analysis in addition to failure analyses. So there is a distinction to be made between the two. So I want to start off by, I want you to think about the following scenarios. So if you look at the image on your left, this is actually taken from a CSB report. The image on the left is actually a tower that's about 200 feet tall, about 30 feet in diameter with 1.5 inch wall steel. And the explosion was so great in this particular plant that it caused one of these towers to fire off like a rocket, as you can see. And so it's quite a sight to see. And you have a unit that was approximately 10 by 10 square blocks, basically, that was left in ruins, as you can see in the right scenario. So when you have an incident like this, you might be asking, well, what are some, if you're not used to the situation, you might want to, consider some things that'll follow kind of coming from an initial incident. So normally an incident will occur and you can have a number of different factors. You could have fire explosion, you could have flooding separately, you can have a chemical release that maybe preceded a fire explosion, but there are a number of different things that could cause an incident to occur. You have your first responders that are going to show up to essentially, they could be doing firefighting efforts, responding to medical injuries, anybody who might have been injured in the scenario. You may even have law enforcement, just depending on the nature of the incident. And if you do have a chemical release or any kind of injuries, then you can expect some regulatory involvement from either Chemical Safety Board, CSB, or OSHA. So those are some of the initial things that can happen very quickly following an incident in which you may have had a fire explosion and a chemical release. So some things that are important to emphasize when you do have an incident of some kind. One of the most critical things to determining cause and origin is preservation of the site if possible, but evidence more so, or potential evidence. So you want to respond quickly and make sure that either the site is secured and you have experts go in that are engaged that can determine safe areas within the site that are accessible, such as structural engineers, materials engineers, chemical engineers, fire investigators, just depending on the specialty required. It's important to be able to determine what parts of the site are safe to access and which parts are not. And site preservation, if possible, can be really important to make sure that you allow all investigators and all parties that would potentially be part of a matter like this the opportunity to be able to conduct their own investigation. If you allow a site or evidence to degrade for too long, then it could make determination of cause and origin in some cases inconclusive. And obviously that's not a desirable condition. I've had situations where sometimes what ends up being key pieces of evidence have been moved to storage outside, exposed to weather and being rained on, and also being close to the coast. And 6 months later, experts are allowed to examine the evidence, and it's been degraded to a point to where it made determination of cause and origin just very difficult and essentially inconclusive, basically. But it makes the investigation harder if evidence is not properly preserved. Often, you might have to consult your legal team or just determine just based on the nature of the scenario. You might want to determine if there's a potential insurance claim or if there are interested parties. Then you'll want to identify those as quickly as possible, and in the course of conducting an investigation, notify those potential parties so that they can get engaged earlier, so that you can allow them to conduct their investigation. But it's always important that if you do have to move things, or if the site does need to be altered in some way, things need to be moved, that those efforts and the condition of that evidence is photo documented or video documented, so that people can review later for their investigation. And scene examination. So as I said previously, in some cases you'll need to notify interested parties if you've identified any. And obviously you'll want to utilize experienced investigators, and sometimes those could be outside investigators, which include certain types of engineers, could include structural engineers, mechanical engineers, any number of engineers you might need to engage, in addition to fire and explosion investigators. So those are some of the experts that you'll potentially need to engage in incident investigation. So as I said previously, why protect the evidence? Well, just looking at an example of a fracture surface, sometimes post-failure, you can see that this is essentially a fracture from a piece of piping. And so there's enough features on there, despite the corrosion that you're seeing on the fracture surface, that you can make out certain fracture features to be able to determine the origin and cracking mechanism, provided that you can clean the fracture surface using some methods in a laboratory to allow you to reveal other things of interest on the fracture surface. If you were to store this outside and expose it to the weather, as I said, in a previous case that I was involved in, the corrosion could be so great that it'll just damage and obscure key features on the fracture surface, making it extremely difficult, if not entirely inconclusive, to be able to determine exactly what happened and why. So just going back to, or just talking about the scientific method, as I previously had indicated, There's 7 steps essentially in the scientific method as defined in FPA 921, and these are essential for conducting a cause and origin investigation, and they can also be utilized in conducting a failure analysis of a piece of equipment or an asset that experienced some kind of a leak or a breach. So you want to recognize the need or define the problem. So essentially in the beginning, something happens, and so you want to basically start off by, okay, so I recognize that there's a need to conduct an investigation. Something happened. Okay, so, I want to look at this piece of evidence. So I need to go through the process of collecting data, kind of doing my examination of what's at the site, determining based on my engineering and scientific training, what kinds of evidence would need to be collected, how you would need to analyze them. And I'm thinking ahead to the different subsequent steps in the process. So when you get to the point of examining evidence or doing a site inspection, you want to do data collection, analyze the data, and then you want to develop ideally, potentially multiple hypotheses in which you can test. And sometimes and often actually testing these hypotheses occurs in a laboratory scenario. And we'll go over that later in the presentation. But through the process of collecting and analyzing data, developing new hypotheses, just depending on the new data information that comes about, you'll test the hypotheses and determine the null hypotheses versus the final hypothesis, which is basically, all right, so I've determined the origin and the cause, or, causal factors and contributing factors. So those are the things, that I'll identify. So the scientific method is essentially, it's important for ensuring that, you're unbiasing your investigation. You don't want to enter an investigation thinking that you know what happened and trying to collect data to support what you think happened. You want to be as impartial as you can, and you want to go through these steps and just, whatever the evidence says is what the evidence says, essentially. And for the cause or for the determination of culpability, that could be something like, was it installed improperly? Was there a manufacturing defect? Did these play a role into the failure, or, was this a process upset of some kind? So those are some of the things that, you can go through and evaluate from a, just outside party scenario. So from an investigative standpoint, prior to reaching a laboratory setting, there are methods that you can utilize to examine or to do a site examination or scene examination. And oftentimes when you have a fire, explosion, or flood scenario, like if you have a water loss of some kind, then using methods such as Part 11 and API 579-1 ASME FFS1, which is a really important document in which the methods can be applied to a number of different applications outside of refining. Part 11 talks about how you can evaluate the condition of materials at a site, just like if I'm looking at different pieces of steel, or if I'm looking at plastic versus paint versus, whatever I might be looking at, depending on the condition of the materials, then you can use these methods to try and determine how hot the material got. So for example, if I'm at a site and I'm seeing warped I-beams, then I can expect that piece of steel was under some loading and got very, very hot over probably in a zone 6 over 1350 degrees Fahrenheit, which softened it, caused phase transformation, potentially annealing, putting it into a condition in which the strength drops rapidly, and you get distortion and warping. And kind of that can help you with determining where did the site get hottest if I'm looking at a fire. So you want to go through and you want to see, okay, so the condition of these materials, this is what these materials are. I can classify them in these different zones and create essentially a heat map, as you can see here, after my categorization. And I can, based on the different zone categories, I can say, okay, so this is the likely probable origin just based on, my examination of the site. So some example applications in which API 579, this part 11 can be useful. It can be useful for a number of things. Cause and origin, I already kind of went over, but also sometimes when you have equipment that's exposed to high temperatures or an explosion scenario, sometimes, it might be tempting to just say, well, throw it out. However, it is possible to use these methods to be able, and also metallurgical evaluation and some other techniques that are in the realm of fitness for service, to be able to determine what damage, if any, if we're talking about a pressure vessel or piping, how hot did it get? I can use different methods to be able to determine if there was some kind of alteration to the material that maybe changed its properties using different metallurgical methods and techniques. And so it's really an important document that can help for basically determine if a piece of equipment is safe for continued use. It could be an important tool for insurance cost adjusting. That's been used in the past in some previous matters that I've been involved with. And you can also use it for essentially determining, safe areas structurally at a site that experienced a fire and explosion investigation. So it's really a very important tool. It can be for various applications. So determination of cause and origin, basically going through the sequence, following the previous things that I kind of mentioned, you'll go through these processes of evidence collection, in which you will identify pieces of evidence to be collected, determining a custodian of that evidence, tagging and logging, and then also ensuring that the evidence is going to be stored in a controlled and secure location that will prevent it from being damaged from the elements or any other way. And then the evidence examination typically is going to utilize non-destructive and destructive methods, which often may take place in a laboratory scenario, and I'll talk about that in just a minute. But when you're going through the process of examining evidence, you're doing various techniques to collect data, whether that's material property data or chemical analysis data, or examining the condition of the material or a piece of evidence that you're looking at. This is the process in which you're developing all of your different hypotheses of, could this have happened? Could that have happened? And then kind of based on the data, you're able to rule in or out different hypotheses to determine cause and origin. And as I said previously, this can be a component or part of a broader root cause analysis, which, as opposed to answering a lot of the how and what questions, which is answered in a cause and origin investigation, root cause analyses typically look into the whys. So as I said previously, a laboratory an evidence examination typically will take place in a laboratory, which is a controlled test space. And what I mean by controlled test space is you can control the conditions in which different analysis and testing is to take place. You can separate essentially the evidence from exposure to the elements. You can, and basically it just is a controlled place in which you can conduct different testing. And large enough spaces, such as the one that we have at BakerRisk, can accommodate multi-party investigations. So you can have multiple attorneys, various representatives, experts present to be able to observe the testing that will be taking place of any evidence collected. So there are different evidence techniques that I mentioned previously, non-destructive and destructive. A few examples of non-destructive methods include visually examining the evidence, not really disassembling anything or cutting anything. It's basically just looking at the evidence as is and photo documenting the condition of the evidence. Following that, some other methods that can be really critical are radiography, if you want to determine if there's any kind of cracking or damage, or wall loss or something that you might see in a pipe, for example. You can also do computed tomography or CT scanning or MRI, and those can be really essential methods for being able to imaging the interior of assemblies prior to disassembly. And that can allow for documentation of measurements. It could be like thread engagement, the position of different internals. You can document that as is prior to any kind of disassembly, and that can be an essential piece of information that could be collected. And you can also do different things like ultrasonic testing and magnetic particle testing to look for cracks or or wall loss or wall variation prior to, cutting any pipes or pressure vessels. Destructive methods, as you can imagine, include essentially disassembly of evidence. If you're talking about, like a system or multiple parts that have been assembled together, an important thing to realize is that you don't want to, once you, like, let's say, okay, so I have, like this connection that came apart. Okay, so I have two separate pieces. Well, you don't want to take the one piece and try and stick it into the other. If, like, let's say you have a solder joint, for example, like a copper solder joint, and it, kind of like split on one side and popped out a little bit, and it's causing a little bit of a leak. You don't want to then, like just pull the rest of it out, because there you're potentially losing some important information. So avoiding disassembly of, any kind of evidence you collected, basically saving that for considering that a destructive method is an important thing to keep in mind. And then obviously some of the other methods that I'll talk about include, cutting and sectioning, metallographic examination, which allows for essentially looking at cross sections of the material to be able to determine, there are a number of things that can be determined, including potential material properties, damage mechanisms, and various other things that I'll get into in a bit. Microscopic analysis, such as if I have to cut something small enough to fit in a particular microscope. And then it could also include, that could include fractography, solvent cleaning. You don't want to just go and start, throwing a bunch of different chemicals on an element or a part. You want to essentially try and preserve that or consider that a destructive method. And mechanical testing also, when you're breaking apart materials, that's a destructive method as well. So an example of some of the laboratory equipment you can see or expect to see in a lab. So you'll have evidence exam tables, you have mechanical test equipment, you have photo documentation stages, and there's just a number of other pieces of equipment. So I just want to highlight a couple of important ones. So in some labs, you'll see a scanning electron microscope, and some people, may not have any exposure or know what a scanning electron microscope can produce. But one of the things that can be really critical information that can be gathered could be, you could look at evidence at very, very high magnifications, up to 250x or greater, which far exceeds the optical limits. So you can only get so much magnification from an optical microscope. Scanning electron microscope allows you to get very high magnification and often good resolution images. And you can look at small scale features, which could be critical to determining a failure mechanism or damage mechanism present. And another interesting thing is that you can use what's called energy dispersive X-ray spectroscopy to do what's called spot chemical analysis. And you can basically look at spots to determine what elements are present. And I'll go over that briefly in a bit. But what can you see exactly? Well, if you look at the top left image, you can see that this is a flea, and like obviously how small a flea is, but that's only a 200x magnification. You can actually get much, much greater magnification, but that's really just an example. Some of the other things that you could determine from a fracture standpoint could be determining if you have a ductile versus brittle overload or ductile versus brittle fracture. That's important because it helps you determine, was there a mechanical overload of some kind, or you seeing brittle fracture? Was there a corrosion mechanism at play, or did you have some form of embrittlement that occurred? And if so, what could it have been? And also, you can do evaluation of fatigue striations, and you can count fatigue striations on some steels to be able to determine likely how many cycles a particular component was subjected to prior to failure. So you can determine a lot of really good visual information in addition to some important chemical information. So for example, as I said previously, you can use that energy dispersive X-ray spectroscopy or EDS to be able to determine elements at a particular spot to see what's present. You can see, for example, in the left spectrum, there's a CL, which stands for chlorine or chloride. So that indicates that you had, like some chlorides present, which could point you in a direction of a particular damage mechanism, just depending on the scenario. So this is all part of the data collection evidence or data collection efforts that are going to take place in a laboratory scenario. If you look at your right image, the top right image, you can see that you can actually create what are called element maps, which will allow you to say, okay, so I have this concentration of this element over here versus this concentration of this element over here. It's another thing you can do as part of your data collection for your failure analysis or cause and origin analysis. And in the bottom, the other thing you can do is called a metallographic mount or a metallographic cross section. You can see that there are numerous cracks in it, kind of right around here and also in this region here. You can use an SEM and EDS to evaluate the composition of the corrosion products in the cracks, and that can help you determine other failure mechanisms. Some other things you can determine include you can do mechanical property testing. So for example, you can do what's called Sharpie impact testing or Sharpie V-notch testing. And what that allows you to do is that you can determine various things about the material, including the ductile to brittle transition temperature. You can determine whether or not under a certain set of conditions, or like in the material's current condition, what is its impact energy, and was it very, very low, or was it a reasonable amount consistent with that particular material? And you can also do bulk chemical analysis of metals, and not just metals, but also plastics, composites, not using this particular method. This method is called optical emission spectroscopy, but there are other methods that are useful for evaluating different types of materials. So then after you've gone through the process of examining your evidence and collecting data, evaluating different hypotheses, and selecting your final hypothesis, which oftentimes you're going to want to determine your final hypothesis within a reasonable degree of scientific certainty, or in some cases based on engineering evaluation or industry best practices. So if you have best practices or codes or specifications that need to be followed, those are some other things that you can consider as well. But for the forensic component, oftentimes if you're going to determine culpability or responsibility for a particular failure, say for example, if something were improperly installed, like there's a bad weld on a pipeline material, or if there was a bad connection at a valve, like could be a valve in a commercial building or something, water valve or a gas line, then those are some of the things that you can kind of evaluate and determine. Was there an installation issue? Was there a material defect? Was there some party that could have been responsible for it? And were codes and standards and best practices used? So those are some important things you can often assess, and you have to consider essentially, the jurisdictional laws in which you're going to be potentially trying a case. So basically, if a loss occurred, you often have to consider, the authority having jurisdiction, what codes were in place at the time of installation or failure, just various things to factor in. So I want to go over a couple examples. This is from a heater coil, which is basically what you had is this was at a chemical plant, and there was some process gas that was running through this coil loop, and it was being heated. So essentially it acted as a heat exchanger. And so they had 3 separate instances of cracking after a 2-year period. You can see in this left image that there are a number of numbered locations where there are cracks, as you can see here. And so there were just clusters of cracks. So what we did was we wanted to evaluate it. So we went through the different processes of visual examination and all the other previous steps that I had described. Some of them we did some NDT, which included magnetic particle testing and some UT. So we were able to collect information prior to cutting into the material. And as you can see here, this is an example of the metallographic examination that I had mentioned previously. So what kind of information can you determine from it? Well, at one of the crack locations where we saw a couple different cracks that were aligned, we cut through them and then mounted and polished them and looked at it under a microscope. And as you can see in this image, some important information you can determine from it includes how the cracks were propagating into the material. So in this case, it wasn't just a straight crack or straight cracks that were going into the material. They were highly branched cracks, and they were also oxide filled. And And so this gives you some data and some information that kind of points you to the direction of a particular failure mechanism. And then following that, we did some analysis of the corrosion products using EDS. And some of the things that we found were sodium, potassium, and chlorides. And so that pointed us into a direction of a couple different damage mechanisms or cracking mechanisms that could have occurred. What also helped was doing basically evaluation by fractography. You can see in this image, we opened up one of the cracks and we were looking at the fracture surface. You can see that the crack is bifurcated, which is also consistent with that branch cracking. But when you look at the fracture surface, this is what's called an intergranular fracture. So this is another piece of information that we collected in the cause or in the process of gathering our data and doing our hypothesis testing and also evaluating what the nature of the failure was. Going through that after consideration of a few scenarios and determining in consideration of also the operating conditions and the age of the components, we considered a number of different factors. We determined that the failure mechanism and the cause for the cracking was an environmental factor. It was caustic embrittlement, and so it's a form of stress corrosion cracking. The environmental issue was, the environmental issue was a causal factor. So we considered the different environmental contaminants that could have been present, and we determined that because of the operation of the this particular coil loop, that it created a condition in which caustics could form, which is why we saw cracking that was kind of favoring one side of the coil. So in this fed into a later root cause analysis, but ultimately an environmental contaminant was determined. But the mitigation essentially was there were some operational conditions that we had advised them of to prevent the cracking. And I think in this scenario, it's important to point out that after the first cracking incident, the coil had just been thrown out and replaced in kind. And so the failure to do a failure analysis in the first place, I think could have saved a little bit of time and additional steps, just because another thing that was determined in addition to some operational issues creating the formation of caustics on the outside of this pipe, we also found that this coil loop had not been stress relieved, but that wasn't something that was determined by the supplier of the coil loop. That was actually at the request of the site. So essentially, in this particular case, we couldn't assign a cause to an installation issue or a manufacturing defect or anything like that. So, but we were able to devise a mitigation strategy which did prevent future failures. And this is a few years ago now. So just briefly, I want to talk about mechanical integrity and fitness for service. What you could do essentially with a fitness for service is a number of things, but basically some of the important information you can get out of conducting the fitness for service includes essentially failure analysis and prevention. You can identify different failure mechanisms that are present. You can basically go through and identify, okay, so if I know these damage mechanisms are present or potential damage mechanisms are present, what can I do to potentially mitigate, those damage mechanisms? And if I am encountering certain damage mechanisms like some corrosion on the interior of a pipe or pressure vessel, then can I safely operate the pipe, for example? This also, or pipe or pressure vessel, and if so, for how long? This also includes if you're finding cracks within a pipe or pressure vessel. Just because you don't have a through wall crack, some questions that you get asked are, at least as it pertains to fitness for service, are can you continue to safely operate? And if so, for how long? And this kind of information can be useful for evaluating inspection intervals, setting inspection intervals, and setting turnaround intervals, things like that. So I wanted to present a second kind of more, it was a failure, but also fitness for service type evaluation that we did previously. So during a turnaround in an acid reboiler, this is a austenitic stainless steel. I believe it was might have been 316 stainless. And what happened was there was some cracking that was found near seam weld that was in this pressure vessel. And so because of the operating conditions and the age, there was a concern over something called sigma phase embrittlement that was happening. So there were a couple things that we did when we were in the process of confirming or evaluating sigma phase, basically the presence of sigma phase. The other thing that was of concern is, okay, so if we are seeing this cracking, what does this mean as far as the condition of the material? So what we determined was that the Sharpie impact testing that we had conducted, we conducted bend testing. We saw that there were signs of embrittlement near the welds. We also saw that from the Sharpie impact testing that there was a 40% shear. So it wasn't fully brittle, but it still had some ductility to it. So that's also an important piece of information that can be used for further fitness for service. But in addition to that, we conducted metallurgical examination and were able to see that, yes, there was sigma phase present, and we were able to quantify the percentage of sigma phase. And that helped feed us into the next question, which had to do with trying to evaluate, is this asset good, until maybe like another turnaround? Do we have to, set some kind of inspection interval for this? Well, feeding this information that we had into the methods that you can utilize in API 579. As I mentioned previously, there's a section part 9, which can allow you to do correlations of impact CBN data to fracture toughness, and you can conduct assessments of crack-like flaws to determine essentially like how big can a crack get before you basically have rupture or fast fracture type scenario, or do you have leak before break, for example? So are you expecting, the leak to occur if you get a through wall crack as opposed to a cross section or piping just rupturing or blowing out? And then also, if you have some information on your materials, as we did in this case, the percent of sigma phase embrittlement, and additionally, an understanding of the load history, we could do fitness for service assessment to be able to quantify number of cycles you can expect and predicting crack extension. Now, in this particular case, you would need to err on the side of caution if you were going to do this kind of assessment, because again, you do have an embrittlement mechanism that's at play. There may not have been any environmental cracking, but your material is expected to continue to degrade. And so it's important to consider that if this is where I'm at now, 40% shear, then full embrittlement is going to take me to 0% shear. So there's some things that you kind of need to keep in mind and ask yourself if you're going to conduct an assessment like this. But in closing, what I covered today, it kind of had to do with different techniques and the use of different techniques and how you can apply them to going through and doing different kinds of investigations with a focus on the cause and origin component. But if there's some takeaways that I can hopefully impart, following a failure, preservation of the scene to the extent practical, in addition to preservation of any potential evidence, is going to be critical. And it's very time sensitive that you act quickly and engage the right people to assist you in that, should you need that, to be able to ensure that the integrity of the investigation is maintained. So then also, how can a laboratory examination aided investigations? I covered a number of different testing scenarios and different kinds of data that you collect, different kinds of things you can determine about, how hot a material got. If you had, like, let's say, multiple potential origin locations, like there was one case where I had where there were multiple explosions at a pipeline. And so determination of the sequence of explosions, was an important factor in identifying, essentially where the origin was, and then really determining the cause. And so sometimes, that's where, as I mentioned, the scientific method can come in, but there are a lot of things you can answer about a material based on its material properties that you can determine from laboratory investigation. And I also covered, outside of, the cause and origin and forensic realm, I wanted to cover the mechanical integrity piece and just mention that if you can identify the damage mechanisms present, Don't make assumptions about a part being old or, well, it probably just cracked because, well, it's a freak thing, so we'll just replace it. Oftentimes, actually doing the failure analysis or doing any kind of damage mechanism characterization can help with identifying a failure or identifying a potential failure and being able to determine, answer questions like, if I find damage, am I safe to continue operating? If I find a failure, how pervasive could this be? Is it localized to one location? How can I inspect? There are a lot of different questions that having a proper mechanical integrity program and also knowing that you can utilize fitness for service methods to be able to determine if equipment is safe to operate. Those are some of the other things that I wanted to kind of provide information on as well. So that covers everything from that I wanted to go over today. I just wanted to kind of briefly say how can we help at BakerRisk. Our group, Mechanical Integrity and Materials Engineering, we currently do all the things listed here, and we can help a variety of clients in legal, insurance, and also operators of facilities. And we can assist in determining a number of different things. And we also have a lot of expertise, not just in conducting cause and origin and investigations and failure analysis, but we also have done joint industry programs. Currently, we're doing an ammonia JIP, and we also provide third-party lab services. So that's basically a scenario in which you can basically just act as an independent lab and facilitate a lab exam to be conducted by other participants and experts and representatives of different parties. So, but that's all I wanted to present today. Again, I wanted to thank everybody for attending this webinar. I hope you found it insightful. And if you have any questions, just please let me know. And if you think of anything beyond today, feel free to email me. My contact information, my email is on this last slide. So thank you.
Great, Sean, and we appreciate your presentation. It was really informative. I am going to go ahead and ask some questions that did come up during the presentation. And just as a reminder to those still on, if you have not already done so, please be sure to type your questions into the Q&A box in your control panel. So Sean, first question, how similar is metals testing to plastics? And can your lab handle more than metallurgical failure analysis?
So the answer to the second question is yes. We are not just a metallurgical lab, but we are a materials engineering lab. So we have the capability to be able to evaluate not just metals, but also plastics, elastomers, composites, ceramics, glass, and we've worked with all categories of materials. And so the testing, there are some similarities between different steps in which you would evaluate, let's say, a metal versus a plastic or an elastomer. But I'd say the principle, but really essentially like the effectiveness of different material characterization techniques comes down to the material properties. So I can examine directly a metal in a scanning electron microscope because it's conductive. However, I have to do additional sample prep, such as sputter coating of a plastic if I wanted to evaluate, let's say, a fracture surface of a plastic. But EDS, as I mentioned previously, would not be a very effective tool for evaluating a plastic. There's actually another category of different kinds of polymers, rubber and plastic characterization techniques that are good for evaluating, organics, different types of base polymers, and you can assess things like thermal degradation, exposure to chemicals, absorption of contaminants, and things like that. But while there are some overlap and similarities where you could do visual examination and you can use some of the non-destructive techniques and some optical microscopy between the two, oftentimes the types of methods you would use are going to be very different.
Perfect. Thank you for that. The next question, do you send people to the site for investigations?
Yes, we do, actually. And so we've been retained numerous times, even outside of a laboratory, to go out to the field and go to a site where an incident occurred and be able to do our own evaluation. And I've been to sites many times because often I know that I'm heavily involved in doing the laboratory aspect of it once the evidence actually comes to the lab and development of protocols and things like that. But in advance of that, if I've been retained by either the site or somebody interested, some party that's interested, I often like to go to the site because there are things that you can tell, and you can conduct your own inspection and scene examination to determine, what kinds of things would be important to collect as evidence. And so being able to, as an expert, get outside of the lab and be able to go to the site and see things for yourself can provide a different perspective than just you just get the evidence that shows up at the lab with not really a whole lot of context. And so you're just you didn't get to see what was at the site or conduct interviews or be able to examine the evidence prior to collection. So we do go to the site. We do those kind of things, and it is definitely very useful for an investigator to go to a site.
Perfect. Thank you for that. Next question. What is the role of a third-party lab? If they are recommended or retained by a particular party, does this create a conflict?
Well, a third-party lab, such as if you're a third-party test lab. So for example, going back to that controlled lab space that I mentioned previously, a third-party lab can facilitate hosting multiple parties, as I mentioned previously, but generally, in a lot of cases, a third-party lab is not supposed to, have, I guess, for lack of a better way to put this, a dog in the fight. Basically, they're supposed to be independently looking at the evidence, collecting data, collecting information, trying to go through the process of conducting the scientific method. But oftentimes, as a third-party lab, you'll be working at the direction of different experts that are going to be involved. And as a third-party lab, it's your role essentially to want to be impartial and not bias yourself to one of the parties. You want to be independent. And so your role is just to, seek the truth, the cause, or essentially the truth, or, the most likely thing to have happened, and identify some scenarios in which, the incident could have occurred. But the role of a third-party lab really is, just to be independent. And now whether or not it creates conflicts, that's more of a legal question. I would say that, if your third-party lab is recommended or selected by, let's say, the plaintiff, for example, there may be some legal questions that I'll defer to attorneys on about that. But for the most part, the third-party lab should be acting as an independent party at the direction of other experts.
Perfect. And it looks like we have time for one more question before we conclude the presentation. So for the last question, did the heater failure happen due to cyclic operating cycles that reached the operating windows?
Yes, actually it did. This was I believe it was carbon steel. I'd have to go back and look at it. But what happened was it was undergoing cyclic operation, and the cracking occurred favoring one location in which we found there was condensation that was forming on the tubing. So it was a daily cyclic operation in which they would actually heat this up to elevated temperature conditions, and then they would allow it to cool, and when they did a shutdown. And as it cooled, there was some caustic that was there were some alkali elements that were getting in there and getting into the moisture and causing caustics that was pooling on that one location in which the cracking occurred. And so as the heater cooled and kind of moved through the caustic embrittlement phase, it would allow for cracking to just kind of occur. And so it can occur very quickly, just depending on the conditions. But in this particular case, there was a cyclic component, and we identified, that these were the factors essentially that were, contributing to it.
Gotcha. And just one more follow-up. I know we were talking about, sending people to sites for investigations, but there was another question, just wondering if our site visits are limited to the U.S. You can just elaborate on that real quick, and then.
No, our site visits are not just limited here. We are an international company, and we have conducted site visits and all throughout North America, South America, the Middle East, and so we're able to go internationally to be able to do site investigations and inspections or whatever's needed.
Perfect. Well, thank you, Sean, and thank you everyone for joining us today. If you have any additional questions, we ask that you reach out to Sean directly, and his information has been posted in the chat. And as a final reminder, today's webinar will be posted to the BakerRisk website, and once a recording is available, you will receive an email from BakerRisk with that link. And finally, we ask that you complete the survey at the conclusion of this webinar. And thanks again for joining us today, and thank you so much, Sean.
Thank you, everyone, for attending.